So welcome to EEE582 Linear Systems, and I will begin with a short overview of this Module 1, which is a linear algebra review. We will talk about linear vector spaces, norms, inner products, and orthogonality. That's the first lecture. Second lecture is linear maps, adjoints, projections, and singular value decomposition. Both of them are fairly heavy in terms of definitions, and some will be new terminology, but it's something that we have to define in the beginning of the course. Then we will see the classical projection theorem and its application to certain least squares and minimum norm problems, which are very important in systems theory and systems application. And we will wrap up the first module with the general case of solving linear systems of equations, and again some applications on systems and how that translates in the things that we want to discuss. By the end of this lecture, the series of lectures on the linear algebra review, we want to be able to identify and characterize problems of the form AX equals B. This is the standard linear system of equations, and it has many applications, especially when A represents not just a matrix, but a linear operator, such as a linear system. Generalization in vector spaces allows us to analyze and get solutions to many interesting problems. We will characterize the solutions of least squares and minimum norm problems, and this is something that you should be able to do easily at the end of the lecture. We should be able to apply the standard formula to compute solutions in the non-singular cases. These are fairly standard cookbook formulas that all need to know, but they have limitations on their range of applications. The general case is number 4, should be able to recognize when to use singular value decomposition to solve the general case, and understand the advantages of computational methods like this. We begin the definitions with the vector spaces, linear vector spaces. What do we mean by that? It's a set which is closed under addition and scalar multiplication. It may sound as strange or vague, but that's the way it should be because it represents a lot of different applications, a lot of different objects. So a linear vector space is closed under multiplication when inside the linear vector space we find a vector and its multiples. If this is the vector x in our big vector space, big X, then 2x should also be part of this linear vector space. The linear vector space should also be closed under addition. So if we think of two vectors, x and y, which belong in the linear vector space, then their sum, x plus y, should be also in the linear vector space. That's the meaning of being closed under addition and scalar multiplication. On the side, the meaning of addition and scalar multiplication must be defined. And if you want the formal definitions, which are a little bit long, you should refer to a textbook or any other reference. These are fairly standard definitions. If you have any questions, how do we define additions and scalar multiplications? These are general operations that we should be able to perform in with the elements of the linear vector space. It also involves the definition of what we mean by a field of scalars. We have to have some properties, and those should be as a part of the formal definition. Part of this definition of the linear vector space, and this is an important one that you should check very quickly. In any case, you need to find whether a vector space has the properties that are required, is whether there exists a zero element or not. The zero element is denoted here by a boldface 0. I will not be able to duplicate that all the time. So sometimes I will use just a plain 0 to denote either the element of the vector space or the scalar 0. But there shouldn't be any confusion arising from that. So 0 has the property that if you add it to any element of the vector space, you get back the element of the vector space. And if you multiply any element by 0, you get the 0 element in the vector space. So 0 would be the origin here in my little graph. As an example of what is not a vector space is a circle. And we can see very easily that 0 is not part of the circle, so it cannot be a vector space. Or you can check the multiplication, the scalar multiplication condition. If I take a vector x and I multiply by a scalar, the result is not necessarily on the circle, on the set that we want to recognize as a vector space or not. Now, beyond the first definition of a linear vector space, what's interesting is to look at sets which are related to that vector space. And the first one is the definition of a subspace. So a subspace is any subset of the linear vector space that is also a linear vector space on its own right. One of the implications of that definition is that it must contain 0, must contain the origin. All subspaces of a linear vector space should intersect at the origin, which means that intersections of subspaces are not empty. Okay, and this is important. Sometimes we do write that the intersection of the two subspaces should have a certain property. It should be just a 0 element. Don't misinterpret that as as an empty set. Intersections of subspaces are never empty. Another interesting structure in linear vector spaces is a variety, which is a shifted subspace. That's getting a lot in the problems, in the optimization problems that we want to solve. So if I have a if I have a subspace V, and some fixed element of the vector space, which is x naught, then this x naught plus V is a variety. It is also called an affine space in certain cases. And we did talk about what subspaces look like, and general sets. They can be circles or disks or any other component that you can think of, maybe quadrants. These are not subspaces. Now some operations on the vector spaces and their subspaces. We're going to look at two subspaces of the linear vector space X, and we will define a sum and an intersection. The intersection is fairly straightforward, is elements of the vector space which belong on both subspaces at the same time. The sum is a little bit different. So the sum is all the vectors that we can get by adding vectors from each one of the subspaces. So looking at R and S, the two subspaces of my vector space, I can form a new set which is going to contain additions of the elements of R and S, and you can take any possible linear combination. So in my example here, the addition of these R and S subspaces gets back the entire plane. So one interesting property here is that both the sum and the intersection of subspaces are also subspaces of the linear vector space that we work on. This is not true for arbitrary operations among sets. So what you would form as a union of two subspaces In my example, the union of the two subspaces would be just the line that forms the R subspace and the line that forms the S subspace. We take the union in the sense of sets. That is not a subspace of the vector space. Another very interesting set here is the direct sum of two subspaces. And this is a sum of subspaces, R plus S, with the additional property that their intersection is just the origin. The way I did it on my little graph here, I had two subspaces R and S. They only intersect at the origin. In this case, the plane, which is my vector space X, would be the direct sum of R and S. There is an important property here that when we can write a vector space as the direct sum of two subspaces, then there exists a unique decomposition of every element of the vector space into elements of the two subspaces. This is a very general property, and we will use it later on when we analyze optimization problems that involve subspaces and linear vector spaces themselves. Making one more step towards decompositions of vector spaces and analyzing vector spaces into fundamental components, we need to define the linear independence and basis vectors. Linear independence refers to a set of vectors So for example, x1, x2 through xn, we're going to say that this set of vectors is linearly independent if the following property holds. If we take any linear combination of these vectors, and it happens to be 0, then it must be that all the coefficients are equal to 0. This implication should go both ways. So if the linear combination is 0, it must mean that the coefficients are 0. And the reverse, which is also trivial, that if all the coefficients in the linear combination are 0, then the sum is 0. This is an if and only if condition. And a standard notation for that is the if with a double F. It's not a typo, but it's a standard way of referring to necessary and sufficient conditions. all the possible linear combinations of elements of a set, we call them span, so the span of x1 through xn is all the vectors which are linear combinations of those elements. The span is always a subspace. And both span and linear independence are not constrained to apply only to finite sets. So you can have an infinite number of elements and question what's the span of this infinite number of elements. One application you probably know already is looking for periodic functions and looking for linear combinations of sets of periodic functions like sinusoids, which give you bases for Fourier series expansions. And now the basis. The basis is a set of elements in the vector space. So xi 1 through n with the two properties. That the elements of the set are linearly independent and their span is the entire vector space. In such a case, n we call the dimension of x. So the vector space has a dimension which is the number of elements that are required to represent the vector space, and they form a basis in the vector space. Examples is, the easy example is R2, which is what you usually see as the plane, with x1 and x2 as the two elements of the basis. But you can also use different vectors to form a basis of R2, and so on. A more interesting case is case of functions or sequences. In this particular case, we look at bounded sequences. So bounded sequence has elements x1, x2, xn, etc. And all of them should have an upper bound. A basis for this linear vector space The basis is also formed by sequences. A first one is the sequence with first element being 1 and everything else 0. The second element of the basis of this vector space is the sequence with first element 0, second element 1, third element 0, and so on. On the side, it's a good exercise that you try to show that what I denoted as L infinity is actually a linear vector space. You have to show that it's closed under addition and scalar multiplication, which is actually a fairly straightforward exercise. If you add up two sequences of this element, of this vector space, you're going to get a new element, which is also a sequence. And if you multiply with a scalar number, you also get another sequence in that vector space, and they're all bounded sequences. After the definition of the elements and some of the general properties of the structure or the topology, as we say, of linear vector spaces, we look at ways to measure distance. It's probably one of the bigger concepts in the analysis of topological objects like vector spaces. And the norm is a map which takes elements of the vector space and assigns a number to them. That number should be non-negative. The norm satisfies three axioms. One is the non-negativity. With an additional constraint that the norm x should be 0 if and only if x is 0. So the only element that has 0 norm, or 0 length if you want, is the origin. Homogeneity is another property which is special to norms. Not all distances have the same property. So if I multiply the element with a scalar, what I get back is the norm scaled by the absolute value of that scalar. And the third axiom is the triangle inequality. And it is named, obviously, because of its relevance to triangles. If you look at a triangle, you add up the lengths of two sides, and they have to be bigger than the length of the third side. Now, these three properties allow us to do a lot of operation in terms of norms, get estimates of bounds of quantities that involve norms. And we will discuss some of them in the sequel. And the big definition here is how to measure distances between elements of the vector space. Another term here, another definition of terminology, what is a normed vector space? And it's fairly self-explanatory. It's a linear vector space with a norm. And in a formal way, we write it as an ordered pair, X and its norm, however that norm is defined. Let's take an example, R3 in this case. So we need the three coordinates. And we can have R3 with the Euclidean norm. Let me give it a subscript. The reason why will appear in a minute. So the norm, the Euclidean norm in R3 is square root of x1 squared plus x2 squared plus x3 squared. The three components of the element in R3, the three coefficients in terms of the coordinate vectors, take the squares, add them up, and take the square root. There is also another norm that I can use, and I will call it x, norm x with a subscript infinity. And this is the maximum absolute value of each one of the xi's. So here I have two different norm vector spaces. I have the norm vector space x is R3 in this case, with the 2 norm. And I have R3 with the infinity norm. Topologically, these are two different objects. One is that they have different properties in terms of convergence of sequences, in terms of how we measure distances. And in general, we can get fundamentally different properties when we look at different norm vector spaces like that. In finite dimensional spaces, the differences usually collapse to nothing. But in infinite dimensional vector spaces, we can get very different results. As a matter of notation, we will talk about the P norm, which is summation absolute values raised to the power P of each one of the elements, and take the P root out of that. In a lot of cases, we will have to combine different types of norms. It will appear a little bit later. We will deal with vector-valued functions. So we will be using norms which apply to function spaces and norms which apply to vectors, and then keeping the notation of the double vertical lines for the norm, it becomes too cumbersome. So in that case, using absolute values with a single vertical line can mean the same thing. Now, where do we use norms? Measuring distances between vectors. But the important thing here is convergence of sequences. So we say that the limit of a sequence of elements from a vector space converges to another element of the vector space in terms of norms is that the norm of the difference between the element of the sequence and the limit converges to 0 as n goes to infinity. This is a very important property because it has translated a convergence in general topological terms, how an element of the vector space converges to an other element of the vector space. It converges that to a question of convergence in numbers. Now, this is a good definition, except that it's not very user-friendly. It's not easy to derive optimization algorithms, recursive algorithms, and show convergence, because it involves the appearance here of the limit of the sequence, which in many cases is not known, or it's the element that we are looking for to analyze. So we define Cauchy sequences. And they have a very mathematical definition. For every epsilon, epsilon is a threshold, there exists an index number, n of epsilon, with the following property, such that if I have two indices which are bigger than the capital N, then the two elements xn and xm are within the threshold, are close to each other below the threshold as measured by the norm that we have. So I can look at the sequence. Here my vector space is really simple. It's just R, and on the horizontal axis I have N, the index number of the sequence. So up here, if you want, is my vector space. Then I can define epsilon to be the desired threshold. And what Cauchy sequences say is that I can find an index after which the difference of any of the two elements in the tail, xn minus xm, could be any of the two elements in the tail of the sequence, and all of them are going to fall within epsilon from each other. They're not sequential elements, they're any two arbitrary elements in that sequence. Cauchy sequences are very important for convergence because it's a convergence test that applies to elements of the sequence, does not involve the limit. And now comes the next definition. The next definition is that of a Banach space, which is a complete normed vector space. What we mean by complete is that all Cauchy sequences converge. They converge inside that vector space, so their limit is also part of the same vector space. They're very important in terms of optimization, again, because what we usually do is construct optimization algorithms that form Cauchy sequences, and we expect their limits to also be part of the normed vector space. Next, we continue with some examples of Banach spaces. And Rn is a typical Banach space with any one of the norms, the p norms that we discussed before. And this is a summation of the xi's absolute value raised to the p power, and take the p root. And the p's can be from 1 to infinity. More interesting object is LP, or little lp in this case, which are sequences. Again, with the p norm, we use the same notation because the definition stays the same. Summation of xi's to the p power, take the p root of all that. P again is between 1 and infinity. But in this case, the little lp are all the sequences for which this norm is finite. In the case of Rn, there is no such issue. We are adding up a finite set of numbers, and we get a finite number out of it. But in sequences, we have to make sure that the sequences in our Banach space have also finite norm. The same applies to functions. And the big LP is the space of integrable functions, so functions where you can define integrals. And the integral of the p power of the function, take the p root of that, is finite. The most frequent norms that we use are the 2, or the Euclidean norm, the 1, and the infinity, which is the max norm. The rest have very few applications, and part of the reason is that they're fairly difficult to compute and they're fairly difficult to do derivations with them. L2 in particular, it's a space that we find a lot in many systems applications, and it's also referred to as the space of energy functions, functions that contain finite energy. So the integral of the function square is finite. An example of a space which is not a Banach space So by this C0, I will denote the space of continuous functions. It is a linear vector space. You add up two continuous functions, you get another continuous function, and so on. And I can consider the normed vector space, which is C0, with the one norm. The one norm being the integral of the absolute value of the function. Then I can form the following sequence of functions. So a function which is 0 between 0 and 1/2. And then it rises linearly in the interval 1/2 to 1/2 plus 1 over n. Takes the value of 1 at the end of the interval and then stays at 1. Okay, so I will duplicate it here. Now, what happens when we change n, when we increase n? Xn plus 1 is the red function, and xn is the blue function. And you can see that the function becomes steeper and steeper. There is the intuitive limit, which is the step function with the step happening at 1/2. And obviously, the step function is not a continuous function. Now, I presented the example in a very intuitive hand-waving function. You actually have to formally establish that this sequence is a Cauchy sequence. So you can see that eventually the area of the difference between the two functions gets smaller and smaller as the slope becomes steeper. So it's a hand-waving argument of a complete proof. And then eventually you can show that under the same norm, this sequence of functions will converge to this step function. However, the step function is not part of C0, of the continuous functions. So we have an example of a Cauchy sequence of functions in a normed vector space which does not converge in the vector space. Continuing with structures on the linear vector spaces, we have norms and we also have inner products. Norms help us define distances between elements of the vector space. Inner products will help us to define some more structure, some more geometry in the elements of the vector space, and in particular, orthogonality. The inner product is another general type of a function with elements of the vector space. Its argument are two elements of the vector space. So it takes arguments from the Cartesian product of the two elements. And in general, it produces complex numbers. There are real inner products where the result of the inner product will be a real number, but in general, the result will be complex. There are 4 axioms that an inner product should satisfy. It should be a non-negative quantity when we're looking at taking the inner product of a vector with itself. So this is the first property, the non-negativity. What happens when we take inner products of the same vector? The second property, axiom, is that of the complex conjugate. So when we change the order of the two elements in the inner product, the result that we get is the complex conjugate of the previous inner product. And that obviously applies only to inner products that are complex. In the real case, that axiom translates to an equality of inner products of two vectors either way. Scalar multiplication. And the scalar multiplication applies to the first element. Recall that changing the order of the elements changes the value of the inner product to the complex conjugate. So the multiplication, the scalar multiplication, should be defined in one of the two elements. And the traditional definition is with the first one. And finally, the decomposition of summations. Examples of inner products. So we can define the inner product between x and y as the summation of xi's yi complex conjugate, which we also write it in short as yhx. H is the Hermitian symmetric component. So instead of a transpose in the complex case, H represents complex conjugate transpose. And for real inner products, y transpose x is enough. When the vector space is L2, so a function space, the inner product is defined as integral of y transpose function of tau x of tau d tau, and you integrate over the interval where the functions are defined. That can be a finite interval or the entire real line, and that's why I don't put any subscripts on the integration. Now, a linear vector space with inner product takes another name, and it's called an inner product space. The inner product space does not have a norm by itself, but there is a norm that is induced by the inner product. And this is simply the square root of the inner product of a vector with itself. As we saw from the first axiom of inner products, this quantity is non-negative and it's zero only if the element is equal to zero. So we can use it as an inner, we can use it as a norm. The actual proof of that is not trivial. It relies on the Schwarz inequality, and it takes several steps. Another name, a Hilbert space. So a Hilbert space is an inner product space which is complete. So it's a Banach space with an inner product if you want, and the norm that we use is the norm which is induced by the inner product. And these are spaces which are extremely important for optimization purposes for the reason that they give you structure in terms of orthogonality, and that allows for computable results, unique solutions, and so on. Examples of Hilbert spaces, Rn, our usual space. When we use the norm 2, this can be written as the square root of x transpose x, very familiar notation here. So this is the 2 norm in Rn, and the Rn with x transpose y as an inner product is a Hilbert space. It is complete. L2 is the space of sequences with a 2 norm, and of course it should be finite. And the inner product, which is defined the way we saw before. So L2 is a Hilbert space. It is complete. But for example, L infinity is not a space which is a Hilbert space, for one, because we don't have an inner product for it. We haven't defined an inner product, or the norm that we use is not the norm which is induced by the inner product. And the big L2 is the integrable functions with finite 2 norms, an inner product which is again defined as we saw before. A little bit of a footnote here. Because we are using the same concepts for either real or complex valued functions, it's a good practice to use the absolute value squared in the integral in the definition of the norms for the case where xi may be complex valued. In that case, just a square is not enough to make that into a positive number. And matter of notation, sometimes we also write the inner product of xy as the dot product between x and y. It's a matter of convenience and usually a matter of context or the tradition of the society who's trying to use inner products. Another little footnote here. What happens when we are dealing with vector spaces which contain vectors in Rn and functions, so vector valued functions? I can think of my element x as being composed of functions x1 of t, x2 of t, etc. up to xn of t. So now I have a vector valued function for which I need to work with inner products, with norms, and in general concepts in the vector space. So here we can look at 2 different possibilities. We can look at defining norms. I change colors here because it will get fairly messy. So I can take the norm in L2 of a scalar function which is the Rn norm of the value of the function at some point. So this is the 2 norm in Rn. Or I can do the opposite. I can take the Rn 2 norm of the L2 norms of the components of this vector valued function. It is a very happy coincidence that the two of these values happen to be the same. Either we take first the L2 norm and then the Rn norm, or the other way around. It works out to the same number. This is not true for essentially any other combination of norms that you might think of in terms of function and vector norms. But the L2 case is the one happy case where this property still holds. And we come to orthogonality, which is one of the most important properties that we will use in optimization. A highly non-trivial result is the Cauchy-Schwarz inequality, where we want to use this result to prove the norm which is induced by the inner product. And what Cauchy-Schwarz says is that the absolute value of the inner product between x and y is less than the product of the two norms. Now, what we get out of the inner product concept is, first of all, orthogonality for Hilbert spaces. And we will write x orthogonal to y to mean that the inner product between x and y is equal to 0. Why is that important? In the context of norms induced by inner products is the Pythagorean theorem. So if I add two vectors, I can use the addition property from the inner product axioms to split the inner product of the sum as four sums, x, x, y, y, and then the two cross inner products, x, y, and y, x. For orthogonal x and y, the two cross inner products become 0. So for orthogonal x, y, the square of the norm of the sum is the sum of the squares of the norms. And we will see very quickly in this group of lectures that this is an amazingly important property, extremely useful to provide optimization results, and it's the cornerstone of the classical projection theorem. For general Banach spaces, we don't have the same concept. there is an alignment property which is defined like this. So when the absolute value of the inner product happens to be exactly equal to the product of the two norms, it means that these two vectors are aligned. Remember, in general, we have the Cauchy-Schwarz inequality to hold. In the case where we have an equality, then we have an alignment of the two vectors. Now, granted that in Banach spaces we don't necessarily have inner products, so here we must define a functional that serves as an inner product. And when we do that, we can get some results, some interesting results in Banach spaces, but the corresponding theory is not as powerful as inner products. A couple more definitions to discuss orthogonality and build on this concept of inner products and orthogonal vectors. When we have a subspace of X, of our linear vector space, we say that a vector is orthogonal to the subspace if and only if X is orthogonal to every element of the subspace. Now, for the subspace W, we may have a basis available. If such a concept exists, then it's enough that X is orthogonal to every element of the basis, for as many elements as we have. If it's orthogonal to the elements of the basis, then it is also orthogonal to any linear combination, which means the entire subspace. Then we define the orthogonal complement of a subspace. It can be an orthogonal complement of a general set, and this is all the vectors which are orthogonal to all the elements of the set. So the definition is very straightforward. What's interesting about the orthogonal complement of a set is that it is always a subspace. And it inherits all the properties associated with subspaces, and part of that is that sequences of elements that converge to an element of the subspace. So again, we can use concepts like this to derive optimization results. We talked about decompositions, and we talked about unique decompositions of vector spaces in terms of subspaces. If we have a direct sum of subspaces, we can write a unique decomposition of every element of the vector space in terms of those two subspaces. A particular case, which is also of particular importance, is the decomposition into orthogonal complements. So if I have S being a subspace, I can write my entire space as a direct sum between the subspace and its orthogonal complement. So looking at my usual space R2 as X, then I can write X as a direct sum of S and its orthogonal complement. Mind you that since we have the orthogonality concept, the only intersection between S and S perp and its orthogonal complement will be the origin. We can also extend the same concept for arbitrary sets. So like I have in my graph here, I can look at R3 so X is R3, the 3D space. And then I can be interested in a subset of R3, which is, let's say, a disk on the plane xy. So if I have directions x, y, and then z up here, I can look at y being a disk on the plane xy. So if I look for orthogonal vectors to every element of y, what I find is y perp, which coincides with the z-axis. So the orthogonal complement is always a subspace. Y itself is not. It's not a subspace, it's just a subset, a general subset of the vector space. Now, what happens if you take another orthogonal complement? So the orthogonal complement of the orthogonal complement. Now this is also a subspace. And this is the smallest subspace that contains y. It becomes equal to y if y itself is a subspace. But in general, it may not be, which is something that we will see when we look at especially infinite dimensional operators which apply to infinite dimensional sets like function sets, function vector spaces. And in that case, the range of the operator may not be a closed set. So the orthogonal complement of the orthogonal complement will have a difference from the original set. Okay, all these will be the subject of future discussions. I will close this lecture at this point and continue with further review of linear algebra in the next lecture.